I'm Paul Schumacher from Air Force Research Laboratory. I'll be co-chairing this session with my colleague Mariba Jah. And as we get into this particular subject, I'd like to refer you back to the keynote speech that Mr. Lavero gave on the first day of the conference. As he was talking about the situation with conjunction assessment and collision avoidance, one of the things he said was, we need better tracking and prediction, and by the way, we need better uncertainty quantification, or we can't even do this thing in the future. I think he's right. I'd like you to keep that in mind for this session, because I think it actually describes this particular set of papers today very well. So thank you for that.
Thanks, Paul. My name is Mariba Jah. I'm the Director for Space Object Behavioral Sciences at the University of Arizona, also co-chairing this with Dr. Paul Schumacher. And piggybacking on what Paul just said, we've heard a lot about space traffic management, and there's a need to know not just where objects are, but knowing what the object is in terms of being able to identify things uniquely. So also keep in mind this idea of tracking, but being able to maintain a label on an object to know it's the same thing and what those challenges may represent. And so this Astrodynamics session, I think, is going to give you a good kind of survey or purview into some of those things. And with that said, we're going to introduce our first paper in this session by Professor Brandon Jones at the University of Texas at Austin, who's going to tell us some great things about GM-CPHD filters.
Thank you very much for the introduction. So first, I would like to thank my co-authors, one of whom is in the audience, Noble Hatton, and then Nick Ravago, who is a new graduate student at UT, and Professor Ryan Russell, who is also in the Aerospace Engineering Department. So to give you an idea of the general multi-target tracking problem, to give you a little context, perhaps for those who aren't as familiar with it as others in the room who are doing active work in this area. We're starting with this notion, perhaps, of 4 objects. We have some PDF describing their location in a single target space. They could be geo objects, LEO objects, whatever the case may be. When we propagate those forward in time, we get some change in the PDF. The increase in the size of, say, the covariance matrix could increase ambiguity. You have more, perhaps, overlap in the possible locations of these objects. Additionally, we could have cases where an object disappeared or died. In our context, it could be due to a breakup, re-entry, whatever the case may be. And we also run into scenarios where we have a new object that may appear, perhaps a newly launched spacecraft or a piece of fragmentation debris. So as we move forward and try to update our knowledge of this single target domain, we get some set of observations. We have potentially some ambiguity in which observation goes to which object. We could have an ambiguity in terms of which one of these objects goes to which target. Maybe measurement 2 goes to 1, or it goes to target 2, and the same with measurement 3. We also have ambiguity in regards to, does target 1, should it use measurement 1, 2, or 3? And then we may have some observation of the newly discovered target, which causes us to need to enact something analogous to initial orbit determination. In multi-target filtering and tracking, we call that birth. So in general, the research in this area in the information fusion community is looking at how do we generalize the notion of a Bayes single target filter to multi-target filtering. So we have some PDF, probability density function, that describes the multi-target state. The multi-target state in our context is the position and velocity, for example, and any number of other parameters for a single target, and the number of targets. This multi-target state, we don't necessarily know definitely that there are 10 targets, 100 targets, 500 targets. That number can fluctuate over time, and our probabilistic representation of this is given by this probability density function. We may have some probability of survival and some PDF describing newborn targets. From that, we get some prediction of our multi-target PDF. From there, we want to update it given some measurements and a probability detection model. We don't always see the objects. We may have missed it. and potential for false observations, clutter. And finally, out of the update, we want a PDF to describe the multi-target state. So it's very similar to what we see in single target filtering, but generalized to many targets and including these processes by which the number of targets can change and when we may miss objects with our observations. So this multi-target filter, a lot of the research currently is looking at parameterizing the multi-target space or state as a random finite set. We'll get into some more of the details in a moment. And once you start with that representation of the multi-target state, it then allows for the derivation of multiple different kinds of filters. There are multiple parameterizations or formulations, and we're going to talk about one of those today. So this obviously has applications to space situational awareness or space domain awareness. But the research that's been going on in the information fusion community, there are certain things that they are able to do that aren't applicable here in our community. For example, they often assume a diffuse prior to instantiate new targets. That works great for airplanes, but it doesn't work for us with new satellites and discovering those. So there's a lot of research that needs to be done in extending the work from the fusion community into our area. So this work really is a combination of several tools that have been developed in parallel or part of this project that have been combined into a single space object tracker, the backbone of which is this multi-target filter. We have previously applied this for geoclusters, but we're, in this paper, extending it to a larger space object catalog. So as I said, we are looking at a simplification or one of these Bayes multi-target filters, the GMC-PhD, and I'll get into a little bit more of what that is in a moment. We've augmented this filter using Astrodynamics-based models, and then we demonstrate its use for tracking 700 objects in near geo. So we use a multi-target filter with what is known as a partially uniform birth model. So as I said, we use a random finite set parameterization of the multi-target space. The idea is that we have some set where each element of the set is a single target state. Position, velocity, it could be orbit elements if you decide to describe the state that way, coefficient of reflectivity, et cetera. And the cardinality, or the number of elements of this set, can fluctuate over time, analogous to birth or death of the targets. And then we observe this through some set of measurements which we group into a random finite set. So this could be all of the measurements from a single optical image on a given electro-optical sensor. So the mathematical tools that are used to start with this parameterization of the multi-target state and derive your filter is known as finite set statistics. You often hear it referred to as FIST. In the information fusion community, you hear it more referred to as FISST now. So the idea is that it does yield a definition in a closed form filter for this Bayes multi-target notion of how we track all of these objects. There are several tractable formulations out there. We are today talking about a partial second-order approximation known as the cardinalized probability hypothesis density filter, or CPHD. And then there are several individuals and universities or companies that have been looking at this, many of which are in this room right now. So the idea behind the GMC-PhD, GM is Gaussian mixture, is that we start with some observation of targets, say geo or whatever the case may be. Through the machinery of the GMC-PhD, we get some description of the density of these targets, some idea of where targets are in space. We also, in this CPHD filter, have a PMF, probability mass function, that describes probabilistically how many objects are in the surveillance region. So in this illustration, we've got 5 peaks, and we've got a peak at 5 objects. So that's the illustration of what's going on here. So the output from the filter is this intensity function, which is the density you see here, and then the cardinality function, the probabilistic description of the number of targets. And we also include object labels in a manner similar to what you see in the literature, which is an augmentation on top of the filter. So I mentioned that we're using what is known as a partially uniform birth model. The idea behind the partially uniform birth model is that we don't make any assumption on where new targets can appear in the field of view. We say that it's uniformly distributed in the field of view. And this is slightly different from the classical presentations of the CPHD. So the idea is that for this birth model that describes where new targets can appear, we have a uniform distribution in the observed direction. So if we, say, are observing right ascension, declination, and perhaps angle rates, if we take the time series and turn it into a 4D measurement, then we have a uniform distribution in that space with some set of bounds. In the orthogonal direction, say in the range and range rate in this illustration, we have some Gaussian mixture that describes our uncertainty in our state in the unobservable directions. So given this birth model, you can then incorporate this into the CPHD filter in a manner that allows for us to use some astrodynamics-based models that we'll discuss in a moment. So one thing I note is that the weight of these new objects in the Gaussian mixture formulation is not a function of the mean and covariance realized in the orthogonal direction. It is a function of the cardinality, the predicted cardinality distribution, your birth cardinality, and then the mean number of newborn targets at each point in time. And I mention this because this allows us actually to reduce the computation time in the filter later. So our combined tracker. So this is a block diagram of all the tools that we put together to form this new tracker as part of this project. So we start with some set of observations. This could be, say, multiple images taken from one telescope over 2-3 minutes, whatever the case may be. From that, we generate what we're referring to as tracklets, where we take those observations, and in cases where we have enough to form these measurements, we create 4D observations. So we're given this set of 4D observations and all the remaining two-dimensional observations. We don't throw those away. We still keep those for the potential that there is an object that didn't yield enough measurements for us to form a 4D observation. We don't want to lose that. So after that pre-processing, we then provide that to the filter itself. So we start with the CPHD prediction, where we're using non-Gaussian propagation of the GM parameterization of the intensity. And then we split the population of targets into two, where one population describes the cardinality and the intensity of all the targets inside of the field of view, and the other one describes everything outside of the field of view. And we do this to prevent what is known as spooky action at a distance. I refer you to the paper to get more details on that, but it also reduces the overall computation complexity of the filter. We have considerably less to process in the update. So we also have a multi-sensor measurement update, and for reasons why we needed to include this, I refer you to the paper, but it allows us to do the Bayes multi-target update with multiple sensors observing the same region in space at the same point in time. That can be complicated and dependent on the order in which you process your measurements. Once we have done the update, we merge the two populations, and then we move forward. So the orbit state and uncertainty propagation. So this work is, a lot of this was done by Noble Hatton and Ryan Russell, and this is really a collection of a lot of force model and numeric integration work that has been developed at UT over the past several years. So we do use the AGIS method popularized out of AFRL, and we combine that with the computationally efficient propagation models. So it includes some work that's been done by Professor Russell on fast evaluation of third body perturbations, rapid evaluation of the gravity field, and leveraged other studies that have been going on at UT. The new propagator is used in the filter, and to create a disparity between the truth and the filter, we use a orbit propagator that was developed at the University of Colorado, CU turboprop, and that was some work I did while I was still with CU. So we have this partially uniform birth model, and we need to take that and we need to get a representation in the range and range rate space for the new targets. So one can use the constrained admissible region, where you have some description based on range and range rate given a set of constraints for where the new targets can be. We use the probabilistic admissible region, which gives us a more accurate representation of the range and range rate hypotheses. And the evaluation time for this, we've got it down to about 5 seconds to generate this. And I note that we only need to generate this whenever that newborn target weight gets above a threshold. So we don't need to do this very often unless it's required. Then there's also a need for robust splitting of the Gaussian mixture model based on the field of view. So in this illustration, which is more not based on a space object tracking scenario, we may have some Gaussian component that is, say, at the corner of the field of view. We have a large amount of mass inside the field of view and a large amount outside. So we extended on a method proposed by Gailey, myself, and Penny Axelrad in a paper to be published in AIAA, where we do a more robust splitting to get a better representation of what the two intensities look like inside the field of view and outside of the field of view. And in this case, we can get that bend in the corner of, if you have a rectangular region in which you can view. So given that splitting of the intensity, we can also split the cardinality distributions. We perform the Bayes update over this portion, merge them later, and move on with the filter. So performance of the tracker for using simulated measurements. So we simulate right ascension declination measurements given 3 ground-based sensors, all electro-optical. And these are using locations at Maui, Socorro, and Diego Garcia. So on the top left, we have, we have the sensor, the schedule for each one of these sensors. So we get an idea of how many objects are in the field of view at each point in time. And then we see the change, the handoff between the sensors over the 24 hours of our simulation. We have the total number of observations on the top right, just over time for those who are curious. And then we have anywhere between about 10 observations of a single target up to a little over 300 in this simulation over the 48 hours. And these are just grouped in ascending order for satellite number. So the first scenario we looked at is with all objects initially known. All 700 are included in the prior and the filter. So the cardinality distribution holds tight at 700. It never thinks that any one of these objects died. It doesn't think that any new ones were born. To provide some idea of the computation cost, we have an illustration of the number of Gaussian mixture components over time, and you see that we never go above 720 in this case. So we stay pretty stable in terms of the number of components required. And on the top right, we have the OSPA accuracy, which is a mean accuracy of the filter over time. And we see that starting at the beginning, we have almost 10 kilometers mean accuracy, and towards the end, we've got an accuracy comparable to our measurement accuracy. So whenever we take 15 of those targets and have the filter not initially know about them, we then reran the scenario to test the performance whenever we start having to include birth. So what we have here, I keep doing that. We have started with 685 targets, and then the true cardinality is in the black here. So you see in the red, we track all the targets. We do have some clutter tracks, but the filter is pruning them off over time. And then we have an improvement in accuracy as we move forward. The spike that you see right here is purely a product of the fact that back here, you have this handoff, or you have this gap between the region visible by both Maui and Socorro, which is then re-seen at that point. So there's some ambiguity with new targets. It quickly removes that ambiguity and converges back to the nominal solution. So with that, conclusions, we combined all these tools to create our space object tracker as part of this work with emergent space technologies. We demonstrated its use for 700 near-geo objects, and we established custody of the newborn objects in the second scenario. There's plenty to do in future work, process real data, expand the test cases, and we've already started this work. So with that, thank you for your attention, and I welcome any questions.
Do you believe there's an advantage to adding to your process fingerprinting or identifying and segregating the objects based on characteristics?
And that is future work that we're actively engaged in right now. I believe there absolutely is an advantage in that.
Our next speaker is Yang Yang from RMIT University in Australia. He'll be speaking to us on the subject of Schmidt-Common filters.
Thank you, Jules. It's a great honor for me to stand here to give a talk. And also thank you my colleagues from RMIT University, student Han Tai and Professor Kofi Zhang for their contributions in this work. Okay. Given the orbit determination problem, it refers to the estimation of orbits of space objects relative to primary celestial bodies given available measurements. This problem has been studied for over half a century, and because it lays the foundation to many other space applications. And it has been improved during last decades because of we have made much improvement in terms of the sensors, the orbit models, and also filtering techniques. So the sensors can provide more precise observations from 100 meters of precision level to millimeter level precision by the state-of-art of the ground-based solar laser ranging system and global positioning system. And we also have more precise orbit models to predict the space object in the orbit. So we have more precise Earth gravity models calibrated by many gravity satellites. And we have also more precise Earth rotation parameters calibrated. And we have put many efforts into the atmosphere drag density modeling, but even the existing empirical models are still far from the true densities. And we have space weather parameters at hand to predict the solar radiation pressure forces. Regarding with the filtering techniques, we also move forward from the beginning least squares to many variants of common filters, like the particle filters, which can be used to deal with both nonlinear and long-Gaussian problems. But so right now, for the satellites, we can achieve centimeter and even sub-centimeter level of optimization performance. However, for more general space objects, when the sensors cannot provide precise observations, and when we cannot predict the orbit very precisely, we have still big challenges to get good orbit determination performance. So we meet with many uncertainties in the orbit models to predict the orbit, like the conservative forces, such as the atmospheric drag and the solar radiation pressure. So when we have these formulas, we need to consider the coefficients which absorb much uncertainty associated with are involved in the modeling. So we need to handle this kind of errors. The first method is to ignore them. However, when this kind of errors are significant, which will lead to, at the most worst case, the divergence of the filter. And we can estimate this kind of parameters together with the orbital states. But when the observability is not enough to predict, to determine both the parameters and the state, this method cannot be used. And we also can consider the parameters. That's the basic idea of the Chimney-Kalman filter we will talk about later. And before we move to the filter, I want to introduce the polynomial chaos expansion, which is a powerful tool for uncertainty quantification. It was first introduced by Norbert Wiener and then extended by Xu with his co-authors to a more general orthogonal polynomial chaos using ASCII scheme. And this method can efficiently characterize the state uncertainty due to the time invariant random parameters like in our orbital dynamics models, the orbital parameters. And this kind of parameters can have any arbitrary probability distributions. So due to this merit, it has been used in the Bayesian framework for state and parameter estimation recently. In the context of PCE, the solution X in our case is the state orbital state, can be represented by an infinite series of orthogonal polynomials. And the phi is the generalized polynomial basis function, and the C represents the PDF of multidimensional random variables. And in practice, we need to truncate the PCE into finite terms. Then we need to solve the coefficients of the PCE. We have two methods. One is intrusive, and the other one is non-intrusive. In this work, we use linear squares regression, which will take the dynamics models as a black box, and then try to solve the coefficients by minimizing the cost function. And then we got here the compact PCE linear systems with the coefficient to be solved. Here the n represents the terms of the coefficients based on the degrees of the polynomial chaos and also the dimensionality of our state. And the m, the index m, represents the samplings we generate to solve the coefficient. And here we illustrate the coefficients, the solutions by propagating the one orbit models. And for the fourth degree polynomials, we have totally 210 coefficients. And the left, And the left figure illustrates the nth multivariate polynomial functions with respect to the degrees of each univariate polynomial functions. And the right figures give plots each PCE coefficients value. So we use the Chimney-Kalman filter to determine the orbit with the models here. And in the orbital models, we have both the state and the parameters, and with also the observation equations. So the basic idea of Chimney-Kalman filter is to reduce the dimensionalities of the state estimate while still consider the effects of the additional states, like the orbital parameters in the calculation of the covariance matrix and the common gains. So in terms of the orbital parameters, they are considered rather than estimated. Like the Kalman filter, it has two steps. One is a time update. Here we have this orbit state predicted using the orbital models, while the orbital parameters are kept as constant, while its variance matrix will be associated with the parameters will be predicted using the state transition metric here, and also the sensitivity metric here. In the measurement update step, it's the same that here the state will be updated using the measurements, while the parameters will keep as constant, but the covariance associated with the parameters will be updated as well. And here's an example to illustrate the chimney compound filter-based orbit determination using GPS observations. In these scenarios, we only use a low degree of EGM, but we consider the orbit parameters, namely the drag coefficient and the solar radiation pressure coefficient. But so we got the OD solutions here, and it has precision level of like less than 1 decimeter in each component. But this precision is the same level with the state-of-art precise orbit determination solution. It implies that with these two parameters considered in the SKF framework, it can also even absorb the uncertainties associated with the lower EGM in the prediction of the orbital models. And since the PCE has two basic merits or advantages, one is that it can quantify any arbitrary distributions of the parameters or state. And the other one is that in the context of PCE, it generates many samplings. So we can use these two merits to and combine the PCE with the SKF scheme to in our orbit determination scheme. We set up orbit determination scenarios with an inclined geosynchronous orbit, and this table gives the force models we used, and we especially considered only the solar radiation pressure in the orbital models. And we generate the ground-based observations using 3 stations two located in Australia and one is in Japan. And we generate the range observations with the standard deviation error of 5 centimeters, and we have the elevation mask of 20 degrees, and the interval is 30 seconds, and we have totally processing time of half an hour. And for the reference orbit, we have the values here as the initial conditions. And for the filters, we add offsets to the positions, like 1 meters in each directions. And especially, we add an offset of 0.2 to the SRP coefficient so that we can test our proposed algorithms to deal with the uncertainty associated with the orbit parameters. And we also have 2 different distributions to represent the SRP coefficient, then compare the effects into the OD solutions. And we got some preliminary OD solutions here, and they're in the Earth center and Earth fixed coordinate system. And we compared the solutions by extended common filter, the SKF, and the filters with PCE. And with these solutions, we found that with the PCE, the OD solutions in especially the X, Y, Z components will become more stable. But still the solutions with the PCE still fluctuate somewhat a little bit. But in this component, the scale is lower than other two components. And in terms of the velocity estimate, the solutions with PCE becomes much more stable. And we have the solution statistics here, and with the PCE, we have more precise solutions in terms of the 3D statistics. Also, the same for the SKF-based solutions. And we use two different distributions to represent the SRP coefficient. And both the solutions are constrained in the 3 sigma threshold, and they just have some difference from the middle of the process. But even the final solutions turn out to be that with the uniform distribution of the SRP coefficient, the OD solutions are even better than the Gaussian distributed SRP coefficient. And we compared different PC degrees in terms of the OD solutions. From the fourth PC degree, the OD performance will become stable. So here's come to the summaries. We have combined the PCE with the SKF scheme, and with the preliminary solutions, we can have more precise solutions with this PCE to quantify the orbital parameters distributions. And but we also need more tests in the future with different orbit scenarios, with different observation types, and with different observation densities. Thank you.
We have a couple of minutes for questions. In that case, I take the chair's prerogative to ask a question.
Okay, thank you.
The polynomial chaos expansion can be quite extensive.
Yeah.
And I was wondering, you have quite low noise levels here. If your noise level is higher, I presume you need much longer expansion to represent the process correctly. Do you have any idea of that sensitivity for your kind of?
It's a good point. Like the PCE can generate to propagate the initial uncertainties and also the process noise. But for the process noise, like once you want to add this kind of noise into the dynamic systems, sometimes it will meet with the curse of the dimensionalities. So it's a really big problem. So in our study, we just as first stage we just ignore the process noise, but we will consider this problem later.
Thank you. Let's
Thank you.
All right, so for our next speaker, we have Moses Chan from Lockheed Martin Corporation.
Okay, so I'm just going to use that. Okay, thank you, Moriba. Appreciate it. So my name is Moses. I'd like to thank you for attending my talk. It's kind of weird here because the spotlight shining on you. For those of you guys don't realize that. So I want to take a moment. Okay, how about this? Is this better? Okay, thank you, guys. So I'd like to take a moment to recognize the contribution of my colleague. The first author of the paper, Dr. Limur Mostad, who is not available to present a talk, and Jonathan, who actually did a lot of the analysis work and prepare for the video, and I get to come to this beautiful island to present the work. Okay, what I have learned in the past is that if I actually tell you what kind of problem that we were facing, then I tell you what we have done. Actually, it works out a little bit better that way. So in many other projects that I have been involved with, that dealing with boosting target, maneuvering target, and even dim target, for example, a lot of the time we do different types of filtering technique, and which lead to very different results. So in this work in here, we wonder how some of these filters would behave with SSA application, SSA images. So what we have done here is formulating the paper with the objective to evaluate ground-based tracking performance of geosensor, with the main focus of comparing and contrasting different filtering techniques. We are utilizing data obtained from the SPOT facility, and I will tell you a little bit more about that. The technical approach in here, for the sake of comparison, have chosen 3 different filters. So I will get into the details, but before I get into that, just sort of give you a little bit of motivation. We start out with an extended common filter, and then we move on to a particle filter because it seems to be more robust with dim target. As all you might have seen, have experience with particle filter is that it has sampling issue. So we bring in the homotopy particle filter, which is originally developed by Fred Dahm and Jim Hahn, and we'll show you some mathematical derivation. Then I will show you the result, and then I will conclude the talk with a summary. Okay, so as I told you, the data was collected from our SPOT facility located in Santa Cruz Mountain in Northern California. And the mission of the telescope is similar to all the other type of telescope that you are familiar with, tracking the space object, identification, characterization, and even doing the interferometric imaging. So the bottom of the chart here has some sort of information regarding the optical performance. So a lot of times, although I know that I'm not presenting the sensor hardware, but this kind of information is important for you to know since we are doing tracking analysis, the spectral band, the field of view, and aperture. Okay, so what you see here on the right-hand corner is the raw images that we collect from the SPOT sensor. The testing data was collected about 2 years ago with a 5-second frame interval. The 11.5-minute tasking interval was chosen to stress the filtering capability in terms of a propagation time. So we find that is appropriate task because sometimes the sensors are located in a very different location. As a result of that, you need to propagate it ahead of time before you can actually correlate it. And also there are times that the sensor is being tasked to do various things. So we want to stress the filter performance with a long propagation time. All right, so the test article here is that start out with extended common filter, but there's some issue with the experiment that we have done with extended common filter. When the system is nonlinear and the measurement is non-Gaussian, a lot of the time EKF doesn't work very well. You sort of have to play with it, put a little bit of TCL to sort of fine-tune the filter. And the more important issue with that is when the target is dim, it's starting to, it will usually lose the target if your detection algorithm is not robust enough. So in this case, we experience that the particle filter is more robust. However, it also has some sort of issue with the sampling. For those of you who have experience with particle filters, sometimes it gets into what is called a degeneracy. As a result of that, the filter solution does not converge. Okay. So we bring in the homotopy particle filter, in which instead of using the sampling technique, we actually compute the particle flow. I will show you how to do that in just a minute. So to evaluate the performance of this filter, we have chosen to use the prediction error in the pixel space and also the processing time, because in some space mission, the processing time is a very important piece of component. Okay, as I told you, the particle filter, now, you have seen a lot of similar depiction of particle filter out in the literature, I assume. The key thing here really is that we are using a set of discrete particles with the associated weight to represent the PDF, okay? Using base rule to compute the posterior by combining the prior distribution and the likelihood of the measurement. So on the lower right-hand column is a picture that we borrow from Fred Dahm and Jim Harm's paper, which they used to describe the sampling degeneracy. So basically, the idea is that if you were to use a bunch of particles to represent the prior and then combine that with your likelihood, it is unlikely that you will come up with a very good posterior. Now, you can resample to try to actually make it better, but then sometimes it actually leads to what is called the impoverishment. What that means is that the particles become too concentrated in a state space. As a result of that, it does not converge to the solution that you want, okay? So the way to get around this problem is to increase the number of particles. Well, you throw more particles in it, you get better result. However, the issue with that is you are going to have to deal with the curse of dimensionality because it does not scale very well together with the dimension of the state space. So homotopy particle filter involves you to define a homotopy. Basically, it's mapping that takes you from one function to another one. Basically, here is from the prior to the posterior distribution by controlling the particles to flow from the state space with a higher likelihood. So the description, the equation is described by a set of partial differential equations. In this case, the Fokker-Planck equations. And that the Q is your diffusion process, which is followed by the equation defined at the bottom of the slide on the left-hand side. Now, the equation seems less difficult, but in Fred Dahm's original paper, they actually solved these PDE and provided a solution. And we took one of their solution set. In this case, it's the non-zero diffusion flow on the right-hand side that we showed you. It actually looks very much like the steepest descent, in which the direction flow go for the particles to the direction that minimizes the log likelihood. And the log likelihood itself is basically a measure of the distance between the expected measurement and the actual measurement. The Haxian of the log P basically is the observed Fisher information matrix. Okay, so enough for equation. Let's take a look at how that might work. So here is a little animation that shows you what the particles are doing. You see the prior mean where the X is, and the particles is trying to converge into the posterior mean. And I will go back one more time so that you can see that. But before I do that, just wanted you to pay attention to the prior mean and the measurement as time goes by, as the homotopy parameter lambda changes, converges to 1, the particle flows toward the posterior mean. So instead of sampling, you're actually computing the flow of the particle, which direct them to the state space where it has the higher likelihood. Okay, so with that, we have this demonstration of the software which is doing what we believe it is doing. On the left-hand side, you have the square which is focusing on the target. And on the right-hand side, it shows you that we construct the orbit. The blue is the truth, the red is the estimated orbital parameters. And there are some parameters in here that shows you how we initiate a filter in case people want to reproduce the result. All right, with that said, let's go into some comparison, take a look at the result. The first thing we would like to take a look at is the elapsed time versus the mean error. So the abscissa of the graph is the elapsed time, which I call propagation time most of the time. And the ordinate here is the mean error in the pixel space. You got to realize there's something called a sawtooth behavior because of such long propagation time. So when you look at EKF, in this case, actually it doesn't perform very well. Now, this chart here is not meant to be saying bad thing about EKF because I myself have had a lot of success using EKF. People might ask that, hey, if you were to use an unsent common filter, you might be able to propagate better. Or maybe if your measurement, the elapsed time is not as long, then EKF would actually work really well. But nevertheless, we wanted to show you this result in here. Particle filter, on the other hand, with 10,000 particle filters, is starting to not, it didn't perform very well. In fact, it's almost like having a degeneracy issue. And then if you increase the number of particles to 1 million to 2 million even, it's starting to perform really, really well. Okay. Homotopy particle filter, on the other hand, utilizing 100 particles, gave us the best result in this case. So the result is actually consistent with what is published out in the literature. So that made us feel very good about that. So in this chart here is to try to compare the number of particles, which is shown on our abscissas, and ordinate has the same value, which is the mean error in the pixel space. EKF is out there by itself because there's only one particle. We call it particle because it is the one filter. And you see that the SIR particle filter, the performance improved drastically as you increase the number of particles. However, there's only so many particles that you can throw at it. Once you pass 2 million, then it's probably not a good idea to keep adding the number of particles. Homotopy particle filter, on the other hand, what you really need is like 100 particles. In fact, I would argue that for 10 particles, homotopy particle filter performs quite well already. Okay, everything that comes with a price, right? So there's no free lunches in here. We wanted to see how well it is doing, but also want to know how long it would take. So in this case in here, we wanted to compare the processing time. The ordinate here is the mean processing time normalized to EKF. So in this case, I don't have to remember all the hardware parameters because I know you guys are going to ask about it, which is a pretty smart thing that we did. And when you look at the SIRP particle filter, actually, when you're using fewer than 3,000 particles, the computation time is actually faster, which is kind of amazing. We believe that has a lot to do with the MATLAB vectorization. And also because we probably didn't spend enough time to try to optimize the EKF code, EKF software as well. For the homotopy particle filter on this end, it actually takes quite a bit of time for us to actually do the computation. So with that said, I will try to conclude my talk with a summary. So homotopy particle filter, I want to say a few things about that. Number one is it uses a lot fewer particles as it has advertised by Fred Dahm and Jim Hahn. It performs a lot better, actually several order magnitude better than the SIR particle filter. However, it does take a little bit longer for us to compute. So our future work is probably involve us to try to optimize the code and take a look at the multi-object correlation. With that said, I thank you for your attention, and I'll take any question you may have.
Yes, hi, thank you. A very interesting talk. I was wondering, could you elaborate a little bit more maybe on the kind of metrics that you used to quantify how much, well, the deviation from the true Monte Carlo approach, I would say, with many 2 million particles would be, how much your approach deviates from that? What kind of metrics you use? Just the mean, the shape of the distribution and uncertainty?
Okay, let me see if I want to make sure I understand your question. Your question is about how do I do the sampling when I were using the SIR particle filter. Is that correct?
No, more the assessment of how good it is. Which metrics you use to assess the quality of your result, the realism of your result compared to using 2 million particles.
And you're talking about Monte Carlo. Well, understand that this is not a Monte Carlo analysis. This is not a simulation. This is actually an experiment utilizing real images.
Okay, then maybe I need to go back and have another look at your paper.
Yeah, maybe we can take it offline.
Yeah,
so
I'll do that, thank you.
Sure. Thank you for your question.
Hey, I was just wondering how the HPF handles multiple objects in your image, because you have kind of this flow towards one region. So let's say you had a bright object and a faint object in one image. I know that's not really the case that you're dealing with, but it's more curiosity for me.
For this experiment, we were focusing on how to characterize the filter. We did not use multi-target in our experiment. Certainly, it's something that we would like to do to evaluate how the filter actually responds or behave in the process of trying to correlate multiple objects. That's something that we will do in the future.
I have a question. All right, I'd like to ask a question. I guess very interesting performance. I saw 100 did a pretty good job with your 100 particles versus a lot more with a regular particle filter. Uncentered common filter is just really a sparse grid approximation when it boils down to it. Do you think that your technique with the homotopy is analogous to just a smart sparse grid approximation kind of filter?
Yeah, I think you can call that a smart way of propagating, but instead of calling it a smart way of propagating it, I like to keep the credit to the folks who actually invented the filter. It is a homotopy computing the particle flow from one function to another. It is a smart way to use diffusion, and there's no reason to change the name of their work. So, thank you for your question.
All right, thank you.
All right, thank you very much, guys.
Our next speaker is Gennaro Principe from University of Southampton. He'll be talking to us on the subject of confidence regions for short arc orbit solutions. I hope I didn't mangle your name too badly.
Yeah, a little bit. Never mind. Well, thank you for your introduction, and I also want to thank you, the co-author of my paper, my supervisor, Sarmelino Lewis. Well, I'm going to talk to you about the confidence region of least square solution for single arc observation. Oops. No, sorry. Well, such a scenario will frequently occur when cataloging small objects like space debris, because in these cases, there can be short observational arcs followed by long gaps before the subsequent observation. Thus, the aim is, in a single passage of the object, to find the solution of the orbit determination problem and reliably describe the uncertainty region. The analyzed scenarios will be with 8 and 15 optical observations acquired in a single passage of the object. So first, I'll give a brief overview about the orbit determination problem, and we'll see how the mathematical technique of differential algebra fits into this context in the computation of the nominal trajectory and the description of the uncertainty region. Then we will evaluate some test cases to see the results of the developed algorithms. Finally, we will draw the conclusions in order to prepare the ground for the future work. Well, in the orbit determination problem, we have some measurements, and we want to find some unknown orbital parameters. When the number of measurements is the same as the orbital parameters, the initial orbit determination is performed. In contrast, when the number of measurements is much bigger, an accurate orbit estimation can be implemented using the least squares or some sequential techniques. When we have short arc observations, we are in the intermediate situation. There is the number of measurements is not so big, although greater than the number of unknowns. In this case, different approaches were proposed, like the unmissable region and this probabilistic extension. What we propose is to use a least squares that exploits all the data acquired by the sensor during the passage of the object. Also, the differential algebra allows us to implement an arbitrary order least squares, as well as to retain high-order terms when describing the confidence region. So, well, briefly, what the least square method is. We have some measurements, a dynamical model, and we want to find the orbital parameters, minimizing the target function j given by the sum of the squared residuals. So we have, for the gradient of j to be 0, we need to solve a system of nonlinear equations, and this can be done by some iterative method like the differential correction. There is a variant of Newton's method. But is the least square solution the only possible orbit? Is the only orbit compatible with the given observations? Certainly not. So are all the orbits with reasonable values of the target function. Thus, the confidence region is computed, defined in terms of penalty to the minimum of the target function, and is outlined by a control value that we call squared k. When we use a second-order approximation to express the target function j, the confidence region is an ellipsoid, whose semi-axes are proportional to the eigenvalues of the covariance matrix. In this case, so the covariance matrix fully describes the confidence region. The least square can also be given a probabilistic meaning. When the sensor noise is Gaussian, the solution of the least squares can be proved to have a Gaussian probability density function. Thus, the boundaries of the confidence region are the level surfaces of the probability density function. And the control value, square k, can be chosen according to the f-test, depending on the confidence level that we want. Well, I mentioned a few times differential algebra, so you're probably wondering what it is. Well, it's an automatic differentiation technique that enables the computation of the Taylor series of functions up to an arbitrary order k. Some DA implementation in computer environment exist, like COSI, developed by Michigan State University, and DACE, developed by the Italian company Dinamica. Let's now apply differential algebra to the least square problem. Well, let's in general how differential algebra allows us to solve a system of nonlinear equations, let's say g of x equal to 0. So first, the evaluation of the function g in the DA framework delivers its Taylor series up to an arbitrary order k. Then we can invert this map and obtain the correction to the state vector for the function g to be 0. And iterating this process, we found the solution of the least squares problem. Well, the solution of the system. When applied to the least squares problem, the function g is the gradient of the target function. So after convergence, the algorithm that we call differential algebra least squares, DALS, provides the solution of the least squares as well as the Taylor expansion of the function j around the solution. This polynomial expression also allows us to use higher order terms when we want to describe the confidence region. But why are these higher order terms so important? Well, what could happen is that when we have short observational arcs, these terms are not negligible. Consequently, the solution statistics will be no longer Gaussian, and the surfaces of equal probability will be no longer some ellipsoids. So, we've seen the importance of computing the boundaries of the confidence region. For this purpose, we devised this algorithm that, given a fixed direction and the polynomial expression of the target function, finds the boundary of the confidence region. So we call this algorithm arbitrary order fixed. Well, what it does, we have the fixed direction. There is the yellow line in the figure. The solution will be in terms of magnitude alpha. If we have a second-order approximation of the confidence region, so the boundary are the red ellipse, we have the solution alpha 2. But if we use the arbitrary order polynomial, we can have a different shape, like the green one. So the solution alpha k can be found numerically using the second-order solution as initial guess. Also, we developed this algorithm to evaluate the evolution of the weak direction, that is the predominant direction of uncertainty in an orbit determination problem, and is given by the eigenvector associated with the greatest eigenvalue of the covariance matrix. This direction plays a major role because it could be used as indicator of nonlinearities, and also, if we have a stretched confidence region, it could be approximated by a monodimensional set along the weak direction. What does this algorithm do? Well, it uses a state-dependent quadratic form along the local weak direction. This means that when we have a second-order approximation, the weak direction is just a straight line, the semi-major axis of the confidence region. But what happens when we use also higher-order terms? State-dependent quadratic form means that the value of the gradient and the Hessian are not just numbers, but they are functions of the point where they are evaluated. So the evaluation of the state-dependent quadratic form at different points along the local weak direction allows us to follow the direction of maximum elongation of the region. Now let's take a look at the test cases that we used to prove the effectiveness of the algorithms. We use the LEO orbits with observations taken every 7 seconds and the standard deviation of 5 arcseconds. We have used the DSTL as a reference for this observation strategy. And also GEO, GTO, and Molniya orbits with observations taken every 2 minutes with standard deviation of 0.5 arcseconds. In these cases, the reference for the observation strategy was TFRM, an observatory in Spain. The analyzed scenarios are with 8 or 15 optical observations acquired during a single passage of the object. Also, we assume the availability of the IOD solution computed with a high-order method, and we consider Keplerian dynamics. In these figures, we can see the observational arcs for the different test cases when 15 optical observations are used, and the maximum angular range is around 7 degrees. Well, I said that the A allows us to implement an arbitrary order least squares, but it has been seen that the inclusion of higher order terms did not improve the convergence properties while increasing the execution time. So we use a second order least squares, resulting in more than 99% of convergence, taking on average 2 iterations. In this figure, we show the statistics of the residuals. Well, we can see that the IOD residuals are 0 at the observation number 1, 5, and 8, as are the observations used for performing the IOG. As for DALS, it reduced the residuals, although using only just few more measurements. The residuals also are more uniform and are compatible with the sensor error. This contrast table shows the median of the absolute value of the error with respect to the true solution. On average, DALS improved the IOD solution, and this improvement was greater with longer observational arcs. But the error in general decreased when the considered arc was longer. As for the confidence region, well, when we use a second order approximation and the covariance matrix fully describes the region, What happens is that the region shrinks when the observational arc gets longer. As these two tables show, they are the covariance metrics for geo with 8 and 15 observations respectively. We can see that the second one, that is related to a longer observational arc, has numbers much smaller, about 1 order of magnitude. But what if we include higher order terms when we describe the region? Here you can see the 85, 90, and 95% confidence region for a Molniya test case with 8 observations in the plane of the eigenvectors associated with the 2 greatest eigenvalues. We can see that the region is no longer an ellipsoid, and also it remains essentially unchanged above order 4. Such a behavior also occurred with the other test cases. Here we can see the GTO, the GEO, and the LEO. Finally, we want to evaluate the evolution of the wick direction. These figures show the projection of the wick direction in the planes of the modified equinoctial elements coordinates for a GTO test case. We compare the evolution of the wick direction when we use a polynomial of order 2 and a polynomial of order 7. In this case, we have 15 observations, and we can see that there's a little change in direction, but it's not very impressive. But this is what happens with 15 observations. When the arc is smaller, like here, well, the direction is significantly bent. And also, we can notice that the red square, that is the nominal, the true solution, the wick direction doesn't catch it. This happens because we only use a monodimensional set. If we had used a 2-dimensional set, this means that not only the wick direction, but also the second weakest direction will be used. So using 2D sets to describe the region, we will get it. So, well, in conclusion, we performed the DARS algorithm at second order because we saw that there were no benefits in using higher order terms. The algorithm improved the IOD solution, although using just fewer measurements. As for the confidence region, the eigenvalues of the covariance matrix that fully describe the regions when we use the second order approximation, they decrease with the observational length. However, the confidence region is not correctly described by the ellipsoid. This happens because the higher order terms in J are not negligible. Finally, we analyzed the wick direction, the evolution, and we saw that it could be significantly bent when we use very short observational arcs. Well, the work done so far aims to be the first step in the initialization of a sequential technique like particle filter that requires the proper description of the confidence region. Thank you for your time.
We do have plenty of time for questions. Okay.
Yeah, I guess.
We'll go back to the mic there.
Yeah, okay, I'll go back to the mic. All right. I guess, no, very, very good, interesting work. Have you also thought about how to extend your technique to be able to do data association?
No, sorry, that is not something that I've done so far.
Okay.
I also have one question. The representation of error in the orbit is best done in some set of elements or something like that. And of course, elements are far removed from the measurement variables, so the transformation is more complicated. Mm-hmm. So maybe there's some trade-off between representing the mapping measurement errors to the state errors, choice of variables must matter for this differential algebra approach.
Yeah.
There must be some best way to choose your state variables.
We chose to represent the uncertainty region using modified equinoxial elements for what will be the future implementation of the work, which means propagation of the error. And as the elements absorb part of the nonlinearities of the dynamics, they could be worth using.
Yeah. Thank you. Well then, let's thank our speaker.
All right, so for our next talk, we have Andre Pack from University of Chile.
Thank you for the introduction. I'm quite honored and excited to be on my first AMOS conference and on my first conference ever. And on behalf of other authors and myself, in the next 15 minutes, I'm going to talk about the work that has been done on Chilbottom radar data processing. So why do we want to do it? And my presentation is going to be divided into 3 parts. First, I'll make a short introduction about why we're doing it, and I will introduce the main source of the radar, the main source of the data. Then I will move on the filter itself, and in the end, I will present the results of satellite tracking. So why do we want to do this? On this image, you can see the partially post-processed data from the radar, and this, the problem of extracting the necessary measurements can be fairly simple for a human eye, but we want not the human, but the machine to do it. So what we are aimed at is we want to convert and to extract the trajectory as seen here from a raw radar measurement that looks like a blue square. And in fact, each vertical line, this blue square, is a return signal strength over the range for every single data acquisition step. So obviously, we want to track and want to reconstruct the trajectory of an observed object, and it has already been mentioned multiple times that we want to maintain a catalog of objects residing in Earth orbit, and as well, the reason why this radar was modified is to serve as a tracking asset for other geographically separated sensors. So, state-of-the-art tracking approaches include multiple hypothesis tracker, joint probabilistic data associations that has been popular since 1980s. Then the recent one include random finite set, and the most novel one, independent stochastic population, and both of them are based on point process theory. So now about the radar itself. So the radar is a fully steerable 25-meter in diameter dish antenna S-band radar located in southern England that was initially used for atmospheric research purposes, but it was recently modified for the use in European Space Agency space surveillance and tracking operations. And it has already participated in European Space Agency CO6 tracking campaign, as well as joint UK-Australian experiment on satellite tracking and data queuing. So on this slide, you can see an example of how the data from the radar partially post-processed may look like. So some of the data sets are corrupted with the presence of blind zone borders, which appeared due to the data acquisition process. And in the first case, we have a single measurement per time step. In the second case, where we tried to process the raw radar measurements by ourselves, it may have multiple measurements per time step. So the reasoning why we have chosen this particular filter is that it exactly fits the problem of tracking with a Chilbottom radar. So it has a single target, multiple measurements. It also accounts for clutter and detection statistics. And as we have a single target tracking problem, there is no need to use multiple target tracking solutions, and it's less computationally expensive than its multi-target counterparts, as well as with proper extension, we can also estimate probability of detection and clutter online. It's a little bit out of scope of this paper, but I will talk about it in the results section. So on this slide, you can see the general workflow that data from the radar goes through. So we have raw radar, then we have either post-processed, initially post-processed, and most of the data set we initially had were provided as pre-processed, or we tried to process, just to extract better detection, we have also tried to process the measurement from the radar with an adaptive threshold algorithm, CFAR. CFAR stands for constant false alarm rate. And we are using these detection sets as an input to the JOT filter that produce our estimates. So as I mentioned, the filter is a random finite set based single target multiple measurement filter. A brief introduction of random finite sets has already been given earlier in this session. And it propagates two things. The first is a target spatial distribution, and the second is target probability of existence. And for the sake of computational simplicity, we're using the Gaussian mixture approximation, where the target state is represented as a weighted sum of Gaussian components, with each of the Gaussian component has its associated weight, mean, and covariance. So as you may know, the Bayesian filter operates within a predict-update loop. So in the prediction state, we have to account for target birth. So the birth is modeled as a Bernoulli process. So with probability of detection, PB, we may have a birth distribution of FB, or with probability of detection minus PB, we may have nothing. Similar to the birth, the survival is also modeled as a Bernoulli set, where with probability of survival, the target may evolve. And the evolved target state will correspond to the Markov transition density, or the target may die with probability 1 minus PS. And similar to the prediction step, in the update step, the measurement is modeled as is a Bernoulli random finite set. And the intuition is like with probability of detection PD, we may have a corresponding measurement likelihood, or with probability of minus PD, we may have no associated measurement. Well, contrary to the measurement birth and survival, clutter is modeled as a Poisson random finite set, and the intuition behind it is there can be a certain number of false alarms, and each of these false alarms having a spatial distribution of kappa. As observation and motion model are highly nonlinear, we are using unscented transform for propagating it in time. So we have a mean and covariance. We approximate the covariance by a set of sigma points. We propagate each sigma point and the mean in time with nonlinear transformation, and then we reconstruct it back. It should be taken into account that in orbital object tracking problem, the Gaussian can be assumed quite carefully, but as the time in between consecutive observation is a matter of milliseconds, we can assume that the distribution is Gaussian. So now let's move on to results. So here is a tracking results for the Cosmos 1939 satellites. As you can see, there was a remnant of a previous reflection in the scene, but it was not considered as an estimate by a target, and the target successfully propagated target state within the blind regions where no target-related measurements were present. And this is a result for a Cosmos 1544 satellite, and as you can see, there was a quite faint presence of a target in the beginning, but it was quite enough to start tracking, and as soon as the target reappeared in the scene, the estimation was corrected. For the data sets that has multiple detections per time step, like the result is presented here. So this is the result for the global precipitation measurement satellite pass. And as you can see, the target was quite faint in the beginning, and the estimation went wrong, but it was correct as soon as target reappeared. This is an example for a same satellite, but a different observation time. Also, the presence of a target was quite sparse in the beginning, so it was not considered as an estimate, but as soon as we have stronger estimation here, we start tracking. On the next slide, you will see a video on how the filter works. So the red crosses the measurement, and the blue arrow and the blue dot is the estimation. So as you can see, it corrects the estimation as soon as it receives appropriate measurements, and it propagates through a blind area, and this is basically how the filter works. And as you can see, there are a lot of clutter measurements that are represented by a red cross. So what we have done, we have presented a real application for a JOT filter, and we have achieved a reliable tracking performance. And also, filter provided an appropriate test bed for multi-target case scenarios. Future work may include we're waiting for some data where we have multiple targets, and I'm not sure if it's possible because channel bottom radar has a quite narrow field of view. We're also looking at implementing an algorithm for a backward smoothing of the trajectory to receive a better estimate of the trajectories that we receive. And we have also completed work on reduced parameterization, as the main drawback of the JOT filter is the high number of parameters to be tuned. So we try to estimate probability of detection and clutter online, so we don't have to guess them or to tune them. And the result of this you can see here. So on the top graph you can see the probability of detection. So you see the first appearance of the target, we have a spike in probability detection. As soon as the target disappears in the scene, we have nothing. So the probability detection is 0. But as soon as it reappears in the closest proximity, we have fluctuation of probability of detection corresponding to the presence of a target in the scene, while it drops in the end to 0 when the target leaves our field of view. And also the clutter, the formulation of the filter that we used did not allow for abrupt clutter fluctuations. So as you can see, when target appears, the clutter rate goes down, but as soon as it disappears from our field of view, the clutter rate goes up. So, and the value of the clutter is expected number of false alarms that we receive. So I would like to acknowledge the Southern Office of Aerospace Research and Development for funding this work, as well as DSTL and STFC and the Chilbotten staff for providing this data, as well as Chilean CONICET and FONDICET funding agency.
Do we have any questions? I guess I have one, and we'll see if anybody thinks of one. So this is very interesting work. Thank you, and congratulations on your first AMOS conference showing. Given kind of the performance with the clutter, the dip that you saw and all that, do you have any thoughts about maybe, because you're computing probability of detection online, do you have any thoughts about how maybe to feed that back to the sensor itself to optimize the sensor performance, which would further help with reducing the clutter?
Well, in this project, we're decided to only receive the data, so we don't have any, we don't have much communication back with people who operate the sensor. And they also, the other drawback is we don't have any ground truth. We have neither the ground truth nor the two-line elements that used to generate the look angles.
Okay. No more questions? Well, let's thank the speaker again.
Our last speaker before lunch is a substitute, actually. Joshua Horwood was scheduled to give this. At the last moment, he couldn't. I assure you that Navraj Singh is equally expert in this subject. He's from Numerica Corporation in Colorado, USA, and he will be speaking to us on the subject of collision risk assessment.
Thank you. Thanks. Right. Thank you for the introduction. So as Paul said, Joshua Horwood could not be here at the last minute due to some personal circumstances. So all the credit goes to him and all the blame as well for this work. But I get to enjoy Maui. So I'm going to talk about Kratos, the collision risk assessment tool in orbital element spaces. This tool we have been working on at Numerica with funding provided by AFRL. And we'd like to thank Apu Bhopale at AFRL for his collaboration. Okay. So the main motivation for this work really is an operational one. There's an operational need to reduce the number of misdetections, the number of false alarms in conjunction risk assessments. So for example, if the probability of collision being reported for a conjunction is much higher than the true risk, that could lead to an unnecessary but costly evasive maneuver. Or on the other hand, if the probability of collision is too low, you could have a missed collision that you could have detected. So there's a desire to perform conjunction assessment further out into the future as well. We have heard anecdotally, for example, that it's desired that conjunction assessment screenings be done up to 7 days into the future in LEO, for example. So that adds to the challenge of providing reliable SSA. So what we feel is that new methodologies are needed that reduce false alarms, misdetections, and in addition provide timely conjunction assessments. So let's go over a little bit as far as what the current practice is. So the current practice, to our best understanding, begins with conjunction filtering, where you take many potentially, many conjunction pairs and try to filter out in a quick and cheap manner all the infeasible conjunctions, and then only do a more detailed probability of collision analysis on the feasible conjunction pairs. So we're not really looking at conjunction filtering. A lot of good work has already been done in that area. What we are focusing on with Kratos is the feasible conjunctions that are left over, and now you really want to compute an accurate probability of collision. Now, what we have found is, before I go there, the current method to actually compute the probability of collision for a feasible conjunction can be attributed to Foster from NASA, Lee Foster, where they make several key assumptions. One of the assumptions is that the state of your primary and secondary object at the time of closest approach is Gaussian. There is an assumption about linear relative velocity and no velocity uncertainty. In addition, however, we found that nonlinear effects actually can lead to non-Gaussian behavior in space. So our approach is really to relax that Gaussian assumption, and our preliminary results kind of show that that is in fact needed in some cases. I should mention before going to the next slide is there are several other approaches. What I really mean by the Foster method here is the Foster formulation. There are methods proposed to actually efficiently calculate the two-dimensional integral in the Foster formulation. So for example, Alfano has an efficient method in use. But they all, according to Josh, that's how he explained it to me, they all are working with the same Foster formulation. That's the two-dimensional integral. So this is where Kratos comes in, where we are trying to provide an innovative approach to compute the PC with having the goal in mind of providing conjunction assessment screenings farther out into the future. So the focus is really on nonlinear and non-Gaussian regimes, although it's applicable to really all regimes. As I hope you'll see that it rivals the accuracy of Monte Carlo-based methods with little added computational cost compared to the Foster method. So the key innovation in Kratos, I've already mentioned, is to think beyond Gaussianity. So what do I mean by that? Not just for the sake of it, but because we have found that the nonlinear effects can lead to non-Gaussianity in the space environment, and assuming making Gaussian assumptions can have negative consequences. So what do I mean by that? So let's focus on the figure on the left here. So shown here is a picture cartoon at the time of closest approach, where shown in red and blue are the covariance assumptions, the Gaussian approximation to the propagated states of the primary and secondary at the time of closest approach. So you can see that there's little overlap. So roughly speaking, this would lead to a low probability of collision. There's no real intersection. But imagine if the true probability density function of this propagated state for one of these objects is this banana-shaped PDF. Well, if you look at that, then you might conclude that there is actually a significant risk here of a collision. So this could lead to a misdetection, this scenario, if Gaussian approximation is assumed. And then the flip side is the false alarm, which is shown on the right side. So Kratos really attempts to treat these banana-shaped uncertainties and other non-Gaussian distributions in an effort to reduce the number of misdetections and false alarms. So how do we do that? The key innovation here is a Gaussian sum representation in orbital element spaces. So there's a lot going on in this figure. Let's begin at the top. So the current practice, as I described, takes the Gaussian approximation for a primary and secondary object at the time of closest approach. That's what's shown here. So we have propagated these to the time of closest approach. And these are represented in ECI now. So now we're getting a little more detailed. The maroon or the red color here is representation in Earth-centered inertial coordinate system. And shown here are also the hypothetical true probability density functions, which are potentially banana-shaped in the ECI space. So Foster's method will take these Gaussian approximations and then output a probability of collision. I'm not going into the detail of what that method is. It is, I think, well known. So what Kratos now attempts to do is, let's say you have two states of a primary and secondary object at epoch, not at the time of closest approach yet, but now we are going to, whatever the state spaces in which they are represented, we are going to convert that into orbital element space, in this case, equinoctial orbital element space, and then propagate this uncertainty in the orbital element space to the time of closest approach. So that's what's shown here. These are the propagated Gaussians in EQOE, that's equinoctial orbital elements, at the time of closest approach. And the reason for doing that is that dynamics are more linear in the orbital element space. So we can actually get away with a Gaussian representation as long as we use an orbital element representation. And shown here is a cartoon of what the true PDF might look like. It's slightly non-Gaussian, but the Gaussian approximation is pretty good. But now the probability of collision is more easily defined in a Cartesian space. You're trying to work with intersections of bodies, so the Cartesian space is more natural. So how do we go about doing that? So at the time of closest approach, once you've propagated your orbital element states, we refine that Gaussian into smaller Gaussians, into a Gaussian mixture. But why do we do that? Because we want to now convert this representation into an Earth-centered inertial space, and that's a nonlinear transformation. So there are two nonlinear transformations here. One is the propagation, the other is now a coordinate transform from orbital elements to ECI. So the smaller Gaussians now, when transformed into ECI space using, for example, an uncentered Kalman transform, but in this case now between a coordinate transform, can still remain fairly Gaussian and realistic, but the Gaussian mixture now approximates this hypothetical banana shape better. Now with this Gaussian mixture in ECI representation for the two objects at the time of closest approach, we can apply the Foster method, the traditional Foster method, on each pair of Gaussians here, and then compute a final probability of collision, which is a weighted sum of the individual probability of collisions, and the details of the mathematics are in the paper. So there are several key points here. The use of orbital elements significantly prolongs the covariance realism. When we are propagating the covariances to the time of closest approach. And the reason for working in orbital elements is that we really gain the computational efficiency there. We could have started with a Gaussian mixture in ECI, for example. So that's a key thing that we're not doing. We could have started with the initial states at epoch, refined them into a Gaussian mixture, and then propagated them forward. But that would lead to an increased computational cost. OK, about 8 minutes. So let's see, with regards to what assumptions we are still making. We are still making an assumption of short encounter time, no velocity uncertainty in Kratos, whereas the Foster method makes additional assumptions, in particular the Gaussian assumption at time of closest approach. Now, we did want to compare our approach with another approach that's inspired by AFRL. You could call it Aegis. It's another Gaussian sum-based approach where the representation is kept in ECI from the beginning. You take the initial Gaussian mixtures in ECI, propagate the Gaussian mixtures to the time of closest approach, and then do something similar to what we are doing here. So let's get to some results now. We'll show a false alarm and a misdetection scenario where in one of the scenarios, we have simulated a representative hypothetical analyst SAT, and another one that's actually representative of a UCT, and based on real UCT data processing, we've simulated a representative UCT. Screening interval of 2 days, and conjunction occurs around 1 day into the scenario. Whereas for a misdetection, we'll show a scenario where the primary is the ISS, that's the real vector covariance matrix state of the ISS, and the secondary object, that's a hypothetical UCT, and a conjunction happens about 2 days into the scenario with a screening interval of 3 days. Okay. So here's a summary of the results. The key point to take away here is that so both Aegis and Kratos are actually within the 95% confidence bounds of a Monte Carlo result. So a Monte Carlo simulation can be done to compute the probability of collision integral more accurately. And the number of samples here or trials determined is based on the Huffding inequality to satisfy a given accuracy. So both Aegis and Kratos are within bounds, whereas the Foster method is leading to an order of magnitude or so of higher probability of collision. And it kind of crosses the threshold of 1e minus 4, which is, we think, the operational threshold for action or decision. For a misdetection scenario, the Foster method actually gives a very low probability of collision, whereas, again, Aegis and Kratos agree with the Monte Carlo result, where the actual probability of collision, according to these methods, is actually much, much higher. In fact, very close to the decision threshold. Let's go to the next slide. So here's a visualization of the misdetection scenario. Shown here is the time of closest approach picture, where the ISS covariance is shown in blue. And also shown here is in purple, kind of difficult to see, the particle cloud of the initial state of the ISS propagated to this time of closest approach. So in this case, actually, the Gaussian representation. Now, this is in ECI. We are actually looking at a 3-dimensional space. This is in Cartesian space, well approximated by a Gaussian. But the UCT propagated to this time of closest approach in the red is the covariance ellipsoid, but the particles follow this banana shape, and it's not really well represented by the covariance. So if you're working with the covariances, you might say there's a low probability of collision, whereas you can see these particles are actually penetrating the ISS covariance ellipsoid. And so the tail probability is sort of pretty high. Foster's method in this case gives a very low probability of collision, so no action would be taken if you were using the traditional method. Whereas with Kratos, you would get a pretty significant probability of collision, which would warrant evasive action. And again, the key point here is that these tail probabilities of intersection can be significant and come close to the decision threshold. So that summarizes the approach, and the details are in the paper. In the path forward, we'd like to relax some of the other assumptions to handle more exotic regimes where velocity uncertainty can be significant, for example. We'd like to automate the process of refining this Gaussian mixture in the orbital element space. And in addition, we want to now actually do some larger studies and determine when does this actually matter, when are decisions potentially affected, what percentage of the time in real data can decisions actually be affected by making these non-linear assumptions now. You might say, okay, this is great, but does this actually affect anything in the operations? But we have shown that you can come up with scenarios quite easily that such decisions can have an impact. In addition, we'd like to now also make sure that the input to Kratos is good. So garbage in, garbage out. Your input states should be realistic, and that gets into sensor-level covariance realism. So to conclude, we've provided a novel approach to compute the PC in order to support conjunction screenings further out into the future. Key innovations are thinking beyond Gaussianity and using an efficient methodology where we do the propagations in orbital element space. And we've shown that traditional methodologies can produce misdetections and false alarms. Tail probabilities can be significant. And so our hope is to provide better probabilities of collision. And with that, I'll conclude and answer any questions. Thank you.
We do have lots of time for questions.
All right. Well, so I guess two things. The first thing is just minor comment. For ages, the whole non-velocity uncertainty thing, when we published the paper, for simplicity, we just did position. Nothing prevents anybody from not using velocity terms, so I just wanted to make that update.
Sure.
For the question, you said you refined the Gaussian mixture in the equinoctial elements and then mapped that to ECI.
Right, right.
Do you conserve the number of Gaussian components during that mapping, or, I mean, as you know, you said there's a significant nonlinearity between the elements in ECI.
Right.
How do you know that that number of Gaussians is the adequate number to represent it in ECI when you do that mapping?
It's a good question, and actually we did present a paper on just that problem. And I can point you to that paper. It has already been presented in an earlier conference, and how to preserve the realism in that orbital element to ECI transformation.
All right.
And the one key point there is that that is actually a much cheaper transformation than propagation. So we can actually get away with many components there. But yet, we do have quantified results as to the accuracy of that.
All right. Thank you very much.
Sure.
Question here.
Yeah, at the beginning of your talk, you talked about longer term predictions like 7 days.
Right.
But, you know, in practice, we find that not very useful just because of the uncertainty in the atmosphere and things like that. But then your examples, you went back down to 2 or 3 days. So
right.
that's what we need is the 2 or 3 days. So I was just wondering if you're really going to pursue the 7 days rigorously, or do you think it's really going to be fruitful?
Yeah, I'll have to ask Josh about that. Whether I guess the assumption here is that yes, your models have to be correct as well. Let's say your models are correct, then can we do something? But you're right that there are so many other uncertainties that all of this accuracy may not matter if your models are not correct out to that time horizon. But yeah.
Okay. I have a question myself. In your examples, you showed the uncertainty volume for the ISS as a covariance. Are you using the Gaussian assumption for the ISS part of your comparison? And I guess my question is it worthwhile to consider re-estimating the ISS orbit in a more nonlinear sense to get a better representation of its uncertainty, or is the problem kind of insensitive to that? Usually the conjunctor is less certain than the ISS, and I was just wondering about if you have a feel for that sensitivity.
I think in this scenario, the ISS, even if we had represented its uncertainty in a non-Gaussian manner, it would have looked fairly Gaussian. So in this scenario, that object was not really represented in non-Gaussian manner. Yeah. But it was the UCT that began with a very large covariance, so it became non-Gaussian very quickly.
Right. Any other questions? Well, I'd just like to add at the end that your comparison with a billion sample Monte Carlo is very instructive, but not every SSA application needs to run on a laptop. In fact, perhaps for an application this important, it's worth parallelizing the whole thing and running it on a big computer and sort of doing it right from the get-go. And I'm wondering, have you thought about parallelizing the Gaussian sum approximations? Because sometimes that sum can get really large, or just do a brute force particle method. I mean, have you looked into those kinds of trade-offs yet?
I think you're right that all the Gaussian mixture methods and the particle methods can be parallelized. So if you have all the computational power, then it may not matter that much. Right. One of the other things that we wanted to point out is the accuracy, right? If you are constrained in terms of the computational power that you have, then you can still work with orbital elements and still preserve some accuracy.
Yes. Okay. Sure. Now, Raj, thanks very much. Let's thank him formally.